Hi guys, so now we are starting the second PowerPoint for Chapter 2. This one is actually about forming compounds, making bonds, and just different things that we need to know about molecules. So, first slide, we're talking about what bonds are. So a chemical bond is a force that holds together the atoms in a molecule or a compound. So there's two types of bonds that we're going to discuss. First of all, we have covalent bonds. Covalent bonds are basically when two atoms share electrons. This typically is going to happen between nonmetals. Okay, that's a key. So if I have two nonmetals like carbon and oxygen, when they form a compound, CO2, it's carbon dioxide, that compound is going to be a covalent compound. The atoms are held together by covalent bonds. All right? And when we have atoms held together by covalent bonds, that's going to give us what we call a molecule. So the word molecule, we're going to, throughout the semester, sometimes we're going to use words not quite the right way, but technically the word molecule can only be applied to a group of nonmetals that are being held together by covalent bonds. Okay, so if we have an ionic compound, which is coming up in a second, a metal and a nonmetal, they don't have molecules. The word molecule should not be applied to an ionic compound. Okay, so what is an ionic compound? Well, basically, if I take two ions, and again, ions are going to be atoms that have charge or groups of atoms that have a charge. So if I have a positive ion and a negative ion, when I put them together, they're going to form an ionic compound. All right, so it's the attraction of oppositely charged particles. Typically, it's between metals and nonmetals, although it doesn't have to be, but most of the time it is. When we write an ionic compounds tend to exist in crystalline form. If they're crystals, then basically you're going to have millions of ions all stuck together. We don't have molecules that exist. We have, basically what we're going to do is we're going to look at the ratio of the positive ions and the negative ions, and based on that ratio, we're going to write the simplest ratio, and that's called the formula unit. So sodium chloride is NaCl. Sodium's a metal, chlorine's a nonmetal. Sodium's +1, chlorine's -1. So if I have a crystal of table salt, it's going to contain an equal number of sodium ions and chloride ions. So the ratio is 1:1, which is why we would say a crystal of sodium chloride, the chemical formula we write down would be NaCl, and the simplest ratio that you could get is called the formula unit. NaCl means one sodium ion and one chloride ion stuck together. They're not a molecule, but it's the simplest ratio of that ionic compound. That's what a formula unit is. All right, revisiting our diatomic molecules we mentioned before. Here they are. Have no fear of ice cold beer is the saying that a lot of people like to use. You need to memorize those, and whenever they come up, those elements by themselves always pair up. And then some of our common compounds. Again, there's a Word document on the shared class files and in D2L that you need to memorize your polyatomic ions and learn some of these common compounds and a few more. All right, so when we write formulas, there are several different ways that a formula can be written. The empirical formula is going to be the lowest ratio of two atoms that you can write for a compound. Specifically, if I have an ionic compound, we always give the empirical formula. Okay, so for sodium chloride, if you wrote down that the formula was Na2Cl2, saying it's a 2:2 ratio, I won't say that the ratio is wrong, but that's not the correct way to write that formula. Ionic compounds always has to be in the lowest ratio possible, which is called the empirical formula. That's how they have to be written. Okay. A molecular formula, though, if I look at the molecule glucose, glucose has a chemical formula C6H12O6. There are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms that are all connected to each other by covalent bonds. If I have that grouping, that's one molecule, okay? And if I write that formula, it's called a molecular formula, it actually tells me how many atoms of each element are present. All right? For covalent compounds, that's how they're usually written. However, there are times that we might want the empirical formula. So if I have the formula C6H12O6, if I reduce that, the simplest ratio would be C1H2O1. So 1 to 2 to 1, which is the same ratio as the 6 to 12 to 6. All right, so it kind of depends on which one you want. Again, most of the time we like to have the molecular formula, but then every once in a while we want the empirical formula, especially if you're doing percentages, because whether I write C6H12O6 or CH2O, they actually have the same percent carbon, percent hydrogen, percent oxygen, because it's the same ratio of atoms. Okay, so that's just something to be aware of. Now, next one we can get structural formulas. A structural formula can be a formula that shows every bond in a molecule in terms of how the atoms are connected. You're not going to learn how to draw those until chapter 8. In chapter 8, we learn to draw Lewis dot structures. Okay. Until then, don't worry about structural formulas. Just know that if you draw out the molecule and all the bonds, single bonds, double bonds, triple bonds, and all that kind of stuff, that's what a structural formula is. And then when you get into upper level classes like organic chemistry, they draw what's called a skeletal structure or a bond line structure, where some of the atoms get hidden, and if you have a chain of carbon atoms, you can actually just make zigzag lines, and at every end of every line there's a carbon atom, and then there are hydrogens that don't get shown, blah blah blah. That again, that's going to be in a later class that you'll eventually learn. All right, so then we have the molecular weight. So if I have a chemical formula, if I add up the weight of all the atoms to get the total, that's called the molecular weight if it's a covalent compound. If it happens to be an ionic compound, then we call it the formula weight. They're really the same thing. We're not always going to be as consistent as we should be between those two, but whether it's the molecular weight or the formula weight, it's just the sum of the weights of all the atoms in the formula. So let's say I have ammonia, which is one of the common compounds that you're supposed to know. Ammonia is NH3. When I look at that formula, you should be able to tell it's 1 nitrogen atom and 3 hydrogen atoms. So if I add up the weights of all those, the nitrogen atom on the periodic table, again, we're always going to use the average weight, because very rarely when we're dealing with a compound are you going to have one atom or one molecule. It's almost always going to be any sample that we can actually hold in a lab, like in a beaker or something, it's going to have millions and millions of atoms and molecules involved. So we use the average weight of nitrogen is 14.01. The average weight of hydrogen is 1.0079 or 1.01, just depending on where you round it. But then you say, okay, but there's 3 hydrogens, so they multiply by 3. So that's the weight from hydrogen, that's the weight from nitrogen. Add them together, that's the total weight. This needs to be a very quick calculation. Most of the time, I do not want you to keep any decimal places. If you look at the periodic table, the average weight of most elements is pretty close to a whole number. So for nitrogen, I would rather you just say 14. For hydrogen, I would rather you just say 1. And then all of a sudden, this problem becomes where right now, if you did this problem, you'd probably need a calculator to figure out the answer. If we rounded to whole numbers and just said 14 plus 1 times 3 is 17, that's a much easier calculation. You can do that calculation in like 5 or 10 seconds. Instead of, if you have to write all this out and use all the decimals, it's going to make it take you a minute or two to figure out the molecular weight. When we get into chapter 3, this is 1 step out of 10 steps that you have to do in a problem, and it can't take that long. So generally, round the weight of the atoms. If they're close to a whole number, round them off. Okay? The only time you don't round them off is if you look at a periodic table, chlorine's average atomic weight is 35.453. Now, 35.453 is nowhere near a whole number. So what I would ask you to do on that is keep 1 decimal place. So 35.453, I'm just going to round that to 35.5. Again, that's going to be a lot faster than using all the decimal places, and students who are having a hard time working through problems, if you also are wasting time on things like that, then all of a sudden, when I give you an hour to take a test, and you're wasting time on things like that, you're not going to be able to finish the test. So this is just advice. Use whole numbers on atomic weights unless they're somewhere in the middle between two numbers, and then keep one decimal place. Okay? So here's a big compound. Question says find the molecular weight of Prozac, which is this chemical formula. So I'm going to talk through it. I don't even know what the answer is, but you can figure it out. But it should be carbon's weight is 12, and there's 17 of them, so it's going to be 12 times 17. Plus hydrogen is 1 times 18, plus 19 times 3, plus 14, plus 16. If you add all those up, that should be your molecular weight. And for some reason I want to say it's 403 or something like that, but I can't remember, so don't quote me on that. All right, so now we get into naming compounds. So we're only going to be able to name by the method we're learning. We're learning how to name binary covalent compounds. Binary means there's only 2 elements. Okay, so if I have 2 elements in a compound, specifically this is going to be nonmetals. Covalent compounds only involve nonmetals. Then basically what I'm going to do, I'm going to name the first element normally. The second element, I'm going to change the ending to IDE. So if I have chlorine and it's the second element in a formula, then I'm going to say chloride. Chlorine becomes chloride. Fluorine becomes fluoride. Oxygen becomes oxide. Sulfur becomes sulfide. Phosphorus becomes phosphide. Okay, so you have to learn those. Really, you don't have to worry about the noble gases because they don't form covalent compounds. So if you look at the rest of the nonmetals, there's about 10 or 12 of them. Make sure you know how all of them change to the IDE, because sometimes it's only a 1-letter change. Sometimes you have to drop the whole ending and put IDE. All right, so I name the first element, I change the second one to IDE, and then I use the prefixes. You have to know your prefixes from 1 through 10. It's in the book. And then the only time I'm allowed to leave a prefix off, if there's only one of the first element, you don't have to put mono in front. Okay, if the first element, if there's only one, you can leave off mono. But the second element always has to have a prefix, and the first element has to have one if it has to have a prefix if there's not just one of them. Okay, so look at an example, P2O5, the first element, the normal name is phosphorus. The second element, the normal name is oxygen, becomes oxide. And then I put the 2 and the 5, that's di and penta. Now penta with the O, pentaoxide is kind of awkward to say. So whenever it's AO or OO from the prefix, you drop the vowel from the prefix. So you just say pentoxide. So, a couple more examples. CO2, we already know you name the first element, carbon, and then there's 2 oxygens, so it would be dioxide. If I have CO, carbon, and then there's only 1 oxygen, so that's monoxide. And then H2O, which we know of as water, but that's actually dihydrogen monoxide. All right, so those are our covalent compounds. The names are pretty simple, especially if you think about ones that you already know. That's a good reference to use. All right, I'm going to go ahead and cut off the video, and then we'll go to the ionic stuff in the next one.